Hello, everyone. Welcome back to another lecture here in Chem 400. So today we're going to start the second half of Chapter 4, which is now we're going to talk more about more reactions in aqueous solution. And the first part of that is redox reactions or oxidation reduction reactions. A very important class of reactions that have many applications, and its use is well known throughout human society and how we live on this planet. Okay, so I would say this is one of the topics that students kind of struggle with. So we're going to go through a lot of examples, and also in discussion we will put our knowledge to the test and see how we do in a kind of like test-like environment where you work on the problems on your own. Okay, so we say reactions where one element is reduced and one is oxidized are called reactions. So these are also called electron transfer reactions, because in the course of the reaction, electrons are transferred from one species or one substance to another, and that change is indicated by something being reduced and something being oxidized. Okay, so two of the most common reactions are combustion reactions, which is the phenomena of pretty much carbon-based compounds reacting in oxygen to produce carbon dioxide and water. So anything that reacts with oxygen gas as a reactant, that's called combustion, because combustion requires oxygen as a fuel. So if you pretty much react anything oxygen gas, that's going to be a combustion reaction. Okay, it doesn't matter if it's carbon atoms. It could even be like hydrogen gas reacting water. That's also called combustion. So it's really anything with oxygen as a reactant, that's combustion. Okay, or like with only oxygen as the reactant and the other substance, that's usually what we call combustion. Okay, so and then electrochemical reactions are also redox reactions, because they have the transfer of electrons, and as we know, as some people may know, that when we move electrons, we generate a current, and that's electricity. So moving electrons, that's the phenomena of electricity. Okay. So here's a classic reaction: methane gas, power, gas heating in homes. You use it to power a heater, and that's the combustion reaction right there. Methane plus oxygen gives you carbon dioxide and water. Okay. So how do we know if something's a redox reaction? Well, we identify a change in oxidation state in the elements. So we haven't really talked about that yet. But we're going to talk about it today. So oxidation occurs when the oxidation number of an atom becomes more positive. So for example, the oxidation number changes from -3 to -1, or +2 to +4. That's oxidation. Reduction kind of sounds like what the name implies. The oxidation number of an atom becomes less positive, so you're becoming less positive, so you're reducing the oxidation number. So I think that one's kind of intuitive, but oxidation might not be. So for example, if the oxidation number changes from -1 to -3, or from +4 to +2. That's called reduction. So we'll mainly focus on assigning oxidation numbers. We're not really going to be concerned with oxidation reduction reactions, like balancing them. I will give you a balanced equation, or I'll tell you to balance the equation that is doable for what we learn, and then I'll ask you, okay, is this an oxidation reduction reaction? If so, what species is being reduced and which species is being oxidized? Okay, so that's our focus for just for our brief talk about oxidation reduction. In Chem 401, you'll learn much more about redox reactions and their applications, and that is called electrochemistry. So electrochemistry is just how like electric cars are touted as green options. They're kind of like the way we want to do chemistry in the future, where we're not using energy that's not renewable. So electricity, that's pretty much a renewable option. But like using heat, gas heating, or like heating in general, we don't necessarily want to do that, I guess, in the future due to our energy needs and concerns for the environment and our wastefulness, I suppose you could put it one way. Okay, so here are some mnemonics to help remember these terms. Oil rig and Leo, or Leo the lion, says Gur. Okay, so oil rig to me is something I remember more better with, I guess. So oxidation is losing. That's what the oil stands for. Rig means reduction is gaining. But it's kind of ironic because oil rig and electrochemistry have really nothing to do with each other. So it's kind of ironic in the sense that we use oil rig as a mnemonic for oxidation reduction, especially when we're talking about electrochemistry. But if you think about combustion, yeah, that's how it works. We isolate oil and we use it to turn into fuel, as fuel and stuff. Okay, so losing is oxidation, or oil oxidation is losing, reduction is gaining. Okay, so Leo the lion says Gur is Leo losing electrons, oxidation. Gur gaining electrons, reduction. So those are kind of two ways we can remember these terms. But if you do lots of problems, like if you do the practice problems that I post, and I will post the next homework probably on Monday. Yeah, probably on Monday or this week, because we'll probably need that practice before the first midterm, which is coming up in like 10 days. So it's getting close. So I should probably think about posting a study guide or review for students. And in discussion, the week of the exam, we will definitely we'll have a review session in the morning on exam day. So I encourage students to come asking questions. Okay. Well, anyway. Okay. So here are the general rules for assigning oxidation numbers. I'm not sure if I'll give I think I will provide these guidelines in a much shorter summary on the for the exam. So you'll have these rules. You don't have to memorize them. You just need to know how to use them to assign oxidation numbers. Okay. So I don't believe in memorization. I guess when I was strict in the past because I had to memorize them, but now that I kind of think about it, it's kind of unfair. But times like 20 years ago, well, not 20 years ago, but more like less than 10 years ago, times were different. Curriculum changes over time, and maybe the educators realize that making students memorize these things is defeating the purpose of learning chemistry. So we don't like to memorize things unless it's absolutely necessary. Okay? All right. So the oxidation state of an atom in any pure form. So pretty much elements on the periodic table, if they're in their natural form, so for any metals, you have just the element itself, like sodium, lithium, magnesium by itself. We say the oxidation state is 0. Now, if you have a diatomic element, that's going to be 0 too. It's like H2, O2, I guess ozone as well, because that's another form of oxygen in the atmosphere, atmosphere. And then P4 and S8 for like phosphorus and sulfur. And then the metals I said, aluminum foil, iron metal, etc. So those will all be 0 because they're just the elements, right? They don't really have an oxidation state because they're not involved in like any compound or with other elements. So we say they are 0. So that's just kind of our like baseline there, baseline value for elements. Okay, so if you have an ion, okay, the oxidation state of the element is going to be the charge. It's going to be the same as its charge. For example, if I have a sodium ion, that's going to be +1, chloride -1. Okay. Now, if I have fluorine, in chemical compounds is always -1. However, if it's fluorine F2 by itself, it's 0. Okay. Other halogens probably usually they have the same -1 oxidation state, but that's not the case when they are combined with oxygen or other halogens, because usually the more electronegative element will have the negative charge or negative oxidation state. Okay, and we'll talk more about electronegativity later on. Okay, hydrogen is another example we have to consider. Is usually assigned an oxidation state of +1 in the compounds when it's with a non-metal. For example, in water, hydrogen is +1, but oxygen is -2. And then when it's paired with a metal, since hydrogen is usually more electronegative than metals, it's going to be -1 because it wants the electron. So that's why it's a -1. Okay. Oxygen is normally assigned an oxidation state of -2 in compounds, with 2 exceptions. If it contain in compounds that contain oxygen-fluorine or oxygen-oxygen bonds, the oxidation state of oxygen is +1. Or, I guess to put it more appropriately, it's going to be determined by the oxidation states of the other elements first, then you determine the state of oxygen. So kind of how like we determine the charges of ionic compounds, of transition metals. We usually assign the charge of the transition metal based on the charges of the anion that is present, right? Or the other atoms present. So the oxygen is the same way in oxidation state. So you might be asking, what's the difference between oxidation state and the charges for the compounds, for ionic compounds? Well, they are kind of similar, but they differ in the sense that they treat bonding in elements a little bit differently. So if you think about charges I think we never really talked about charges yet. So it's kind of like what you think about in ionic bonding. You have charges on ions, and that's because electrons are usually associated with the anion, and the metal has no valence electrons, so it becomes a positive charge. It loses electrons to become a positive charge. And that's kind of what we're doing here with oxidation numbers. The more electronegative element will have the negative charge, and the element that gives up those electrons will have a positive charge. Just like in ionic compounds, the metal bears the positive charge, loses electrons to the more electronegative anion or atoms of an anion, and that's why it has a negative charge. But when we talk about formal charge and talking about drawing molecules, we'll revisit the idea of how charge is defined for two different concepts in chemistry. Okay. All right, and lastly, the sum of the oxidation states of the atoms in a neutral molecule or ion must equal the charge on the molecule or ion. Okay, so for example, if I have nitrate, NO3 minus, the oxidation states of nitrogen and oxygen, they must equal the total charge of the nitrate ion, which is -1. Okay, so let's try some examples. All right, so... All right, assign oxidation numbers to the atoms in the following compounds. Aluminum oxide or alumina, which is used in pigments, ceramics, and abrasives. Xenon tetrafluoride, one of the first rare gas compounds. So xenon is a weird molecule. It's a noble gas, but it turns out it does like to form bonds to other elements, and that's pretty much the only noble gas you'll ever see that has compounds. You never see compounds of helium, neon, or argon, or like even krypton. You don't even see those. So xenon is the interesting one. And then lastly, potassium dichromate, which is we talked about this before. It's one of the principal components in the breathalyzer test, used to determine if someone has been drinking alcohol. Right, A. So aluminum oxide. Okay. So we know aluminum, right? If we go back to our rules here, none of these elements are by themselves. So there's no aluminum metal, there's no oxygen gas. So the oxidation states are going to be a little bit, they're going to be non-zero in this case. So aluminum, we can think about aluminum in the terms of their charges in the ionic compound. Okay, so oxygen usually has a oxidation state of -2. So we're going to say oxygen -2. Okay, and then aluminum, like in how we named ionic compounds, aluminum is going to be +3. Okay, so the sum of these oxidation states should equal 0, but they don't equal 0 right now if we just consider one atom. So we have to consider the sum of the atoms in the compound. So we have 2 times +3 plus 3 times -2. So we get 0. Okay? So that's that. So aluminum oxide is going to be +3 for aluminum, -2 for oxygen. So even though there's 3 oxygen atoms in there, we don't say it has an oxidation state of -2. We're talking about the oxygen atom itself. Each oxygen atom will have an individual oxidation state of -2. So we don't say -6, and we don't say aluminum is +6. We say aluminum is +3 because in the ionic compound, aluminum would have a +3 charge per aluminum atom, and then oxygen will have a -2 charge per oxygen atom. Okay, so we don't say +6 or -6. All right. So xenon tetrafluoride. So xenon is a peculiar case. So we're not going to assign that oxidation state yet. Okay, so we're going to wait a bit here. Okay, so first let's assign fluorine's oxidation state. So let's go with fluorine first. So we know fluorine usually has a oxidation state of -1 here. So it's always -1. So fluorine, you could always think when it's in compounds, fluorine's in compounds, is always -1. So we're going to say -1 for fluorine, okay? So in this case, the total charge there will be -4, right? So fluorine, -1 oxidation state, but you see here we have 4 of them, so we need, we have a 4 times -1. Sorry, let me just write this a little bit differently. So 4 times -1, that gives us -4 charge, right? So now xenon should be, the oxidation state should cancel out the -4 because xenon tetrafluoride is a neutral compound. So we probably should say, we could conclude that xenon is going to be +4. And when we do that, we get +4 4 plus -4 gives us 0. So our total oxidation number equals the charge of the molecule xenon tetrafluoride, 0, the charge. So we're good. Okay, so fluorine will be -1. It'll give us a total of -4. So xenon should be +4. Okay. Now, as a trickier one, we have 3 different atoms now. So potassium dichromate. Okay. So we should number the charges we know first. So potassium in its compounds is usually +1. So we're going to label potassium +1. Because in this form, right, it becomes 2K plus, and then Cr2O7 2 minus. So that's the total charge of those ions. So K should be +1. And then now we have chromium. We don't know chromium yet, so we're going to leave that blank for now. And now we're going to have oxygen. So remember, oxygen, unless it's bonded with a halogen or another oxygen, we can't determine its oxidation state. But since it's not bonded to another halogen or oxygen, we can say it's -2. So oxygen will have an oxidation state of -2. Okay. So we have 2 potassium atoms. And then we have 2 chromium atoms. Plus 7 times -2. Okay. So if we do some algebra here, this should all equal 0. So if we rearrange the equation here, we get 2Cr equals let's see here. What am I doing again? Let me see. Okay. Oh, right. So equals 14 minus 2, because the 7 times -2 will give us -14, so we add 14 to both sides, and then subtract 2 to isolate the chromium here, and then so we get, over here we could divide by 2, Cr equals 12 over 2, which equals +6. So each chromium atom should be at a +6 oxidation state. So we say chromium has +6, paired with the 2 chromium atoms will have a +12, then 2 chromiums +2 for a +14. That will cancel out the -14 charge that is given by the 7 oxygen atoms here. Okay, so that's how we assign oxidation numbers. It's kind of similar to how we named ionic compounds, where we consider the charge of the ions, then figure out what the charges should be based on the chemical formula. Okay? All right. So that is part 1 of this lecture for oxidation numbers. We're going to continue this discussion in the next video. So I'll see you then.